This is part 2 of section 11.3, area of circles and sectors. We've just gotten finished with examples 1, 2, and 3. Now we're on example 4. What is the exact and approximate area of the shaded circle segment? And it's kind of hard to see here, but this is it right here. Little tiny thing. Round your answer to the nearest tenth. Okay, so another circle segment problem. As example 3 was, we have the area of the circle segment. This time it's circle segment AB. So the area of circle segment AB is the area of the sector that it belongs to. That's sector ACB. This sector right here, piece of pie, so to speak, minus the area of the triangle that corresponds to it, which this time would be this triangle right here, triangle ACB. So, the area of a sector formula says that you take the measure of the arc, so the measure of arc AB over 360 or 360 degrees is a ratio, multiply that with the area of the whole circle, pi r squared, minus the area of the triangle associated with it. The area of a triangle is 1/2 base times height. So we come over here and to find our variables, we have our radius, which is 18 inches. We have the measure of arc AB we need, which it's not here, so we go to the central angle. It's 60 degrees here, therefore the measure of the arc is also 60 degrees. Then for the triangle, we have base and height. The base of the triangle is 18. The height, that's the issue on this one. Take a look at the triangle. We don't have a height for it yet. Notice this is 60 degrees here. If we pull that triangle out, and if we draw an altitude from point A straight down, perpendicular to the opposite side, not only do we form a 30-degree angle here, because this divides this angle into two parts, but also this is congruent to this now. Well, the whole CB was 18, so now divide that by 2, and we have 9 for each piece of this side right here, the base. So this would be 9 for the short leg of a 30, 60, 90. So we take the 30, 60, 90 triangle theorem. The ratio is 1 to root 3 to 2. Short leg, long leg, hypotenuse. And in our right triangle, the only side we have right now is the short leg 9. So we put 9 under the 1. We are looking for the height right here of the triangle. It's right here. So that's the long leg. It goes under the square root of 3. We don't need the hypotenuse on this one. Okay, then, well, I just noticed you could have used 18 here because all radii in a circle are congruent. So this is 18 also, and you could have used 18 here. So you could have done it that way too. I'm going to use these two. So pull those out. I have 1 is to 9 as root 3 is to h. Cross multiply, we get 1h or h equals 9 times the square root of 3, and that's our height. So I'll place this in here, 9 root 3. Now we have everything we need. We come back over to our formula. Starting with the measure of arc AB, of course that was 60 degrees. So we have 60 degrees over 360 degrees times pi times the radius, which was 18 squared, minus 1/2 times the base of the triangle. Now that was 18. It wasn't 9. It was 18, the entire triangle. So that's 18 times the height of the triangle, we found was 9 root 3. Next, as we start to simplify this, be very careful. Notice that 60 over 360 divides out by 10, so we get 6 over 36 times 18 squared is 324 pi, minus, notice that the 2 and 1/2 will divide out with the 18, so 2 goes into 2 once, 2 goes into 18 9 times. Now we have 1 times 9 times 9 times root 3, so that's 9 times 9 root 3. 636 reduces by 6. 6 goes into 6 once. 6 goes into 36 6 times. We have 1/6 times 324 pi minus 9 times 9 is 81 root 3. Next, 6 and 324 are divisible by 6. 6 goes into 6 once. 6 goes into 324 54 times. So now we got rid of our fraction here, so now we have 1 times 54 pi, or 54 pi, minus 81 times the square root of 3. Now, this is a pi term, this is a square root of 3 term. We cannot subtract these and get an exact answer. So this is our exact area. 54 pi minus 81 root 3 inches squared. They did ask us to approximate also. So the area of circle segment AB, be careful, 54 times second pi, enter, minus 81 times the square root of 3, enter, and you should get 29.3 approximately inches squared. So there are almost 30 square inches in this little circle segment here. It's a pretty large circle. Example 5. We're going to do a little composite area now. Write a simplified formula to find the area of the shaded region. And the shaded region is not just each part of these, but the whole thing together. So it's these little corners all together. Then find the exact and approximate area of the shaded region in the figure. Find the exact answer in terms of pi, and the approximate, or find the approximated answer to the nearest hundredths place this time. Okay, so first of all, since we've got a composite, the area of the composite here, in general, we have a square. The square is bigger than the circle. Generally, when you have to subtract something out, which we're going to have to do here, we're going to have to subtract the circle out, you take the larger figure and then you subtract the smaller one. That's not always true, but it's true many times. So we're going to take the area of the square first, SQ, and we're going to subtract out the area of the circle. So we come over here and we define our variables. For the square, all we need, if you'll recall, we can use A equal base times height, but since base and height are the same in a circle and a square, then we can use A equal S squared, side squared. So I'm just going to use side, S for side. So S, the side length, of course, is 2 feet. And then for our circle here, our radius, since this is 2, and this is 2, that means from here all the way across is also 2. That's the diameter. So the radius is half of that, and the radius is 2, or excuse me, the diameter is 2, divided by 2, you get 1. So the radius is 1, and the side length of the square is 2. We have what we need now. We come back over here. We get area of a square is S squared minus the area of a circle is pi r squared. Notice we don't have any variables that are alike, so there's nothing to simplify. This is the formula for finding this shaded region right along here. Next, we find the actual area by substituting in the values. S is 2 squared minus pi times the radius, which was 1 squared. 2 squared is 4, minus 1 squared is 1, and 1 pi is simply pi. So 4 minus pi, and of course we can't combine those, so that's 4 minus pi square feet for the area of this composite figure. That's our exact. Now for our approximate, Take your calculator and calculate 4 minus pi, and you'll get approximately 0.86 square feet, rounded to the nearest hundredth. Example 6. More on composite area. Write a simplified formula to find the area of the composite figure. Then find the exact and approximate area of the composite. Find the exact answer in terms of pi and approximated answer to the nearest tenth place. Okay, so we've got this particular shape here. We first noticed that the shapes that are involved here. We've got a big trapezoid here. We also have part of a circle. In fact, it's exactly half a circle, or a semicircle. But we also have a smaller circle that shares the same center that we're going to need to subtract away because it's not part of our figure. So, to start off with, the area of this composite, we're going to take the area of the trapezoid. To that, we will add the area of the larger half circle. Now, the larger half circle includes everything that's inside here also, this whole thing right here. The circle would be the whole thing, so we're going to need to take half of that. We add half the area of the larger circle, or I'll call it the outer circle. Now, as it stands right now, we'd be finding the area of everything inside here, including this little area right here. So now we need to subtract out this smaller circle. So we subtract, and it's not the whole circle, it's just half the circle, or the semicircle. So we subtract half the area of the inner circle. So this is a general formula, what we're going to use before we use our dimensions. Now let's define our dimensions. Trapezoid, start with that one. We're going to need base 1, base 2, and the height. I'm going to let this bigger base be our base 1, so that's 36. Our base 2 goes from here to this point all the way over to here. We don't have a direct measurement there, so what we're going to have to do is take note of the circle here. Its radius, this inner one, is 2. Well, if it's 2 here, it's 2 here. And from here to here is 4. So actually, the radius of this bigger circle is 4 plus 2, because it has to start from the center. We'll get to that in a minute. So this is 2, and this is 4. Well, it's also 2 on the other side here, and it's 4 here. So far we have 4 plus 2 plus 2 plus 4. Then these two are congruent, and I forgot to I printed this on the sheet, but I forgot to put it on here. It's 4 inches. This is 4 inches, and it's got a tick mark in it, so this is 4 inches. So we have 4 plus 4 plus 2 plus 2 plus 4 plus 4, or 4 times 4 plus 2 times 2. And so that gives us 16 plus 4, which gives us 20. So 20 is our base 2. 20 from here all the way over to here. Okay, then our height is given to us. It's 8. It's perpendicular to both. Okay, now for the semicircles. For the outer one, our radius is all we need for this, for our area formula. So the radius would be 4 plus 2, which is, of course, 6. So our radius of our outer circle is 6. The inner circle, the radius is 2. Now, since we have two r's that are going to be in our formula, we need to show that they're different, so we use numbers, sub-numbers. I'm going to call our outer radius, radius 1, or R1, and our second inner radius, radius 2. That one and that one. So we've got everything we need, B1, B2, H, and then R1 and R2. Now we write the formula in detail. The area of a trapezoid is 1/2 times the height of the trapezoid times the sum of the two bases, B1 and B2, plus 1/2 times the area of a circle, pi r squared, but this is the outer circle, and the outer circle's radius is R1, minus 1/2 times the area of a circle again, pi r squared, except this time it's the inner circle. The inner circle is R2. So we have this right here is our formula. We need to try to simplify. So, to simplify this, I will notice that we have 1, 2, 3 terms. They're all separated by addition or subtraction signs. All 3 of these terms have a 1/2 in common, so we can factor out a 1/2. So 1/2 times what's left, H times B1 plus B2 plus pi R1 squared minus pi R2 squared. Now, there's one more thing. These last 2 terms have a pi in common. Now, we can't take a pi out of this term, there's no pi in it, but we can take it out of these 2. So what we would do is we would write 1/2 times, when this stays the same, H times B1 plus B2 plus, and then out of these 2 we take out a pi and use parentheses for the rest of it, R1 squared minus R2 squared, and then close the bracket. This is the formal simplified area formula for this particular composite figure. Okay, now let's go ahead and find the actual area using values that we know. And so here we go. We have 1/2 times the height was 8 times B1, which was 36, plus B2, which was 20, plus pi times R1. R1 was 6 squared minus R2 was 2 squared. Close parentheses, close bracket. Then, carefully solving this, we need to do what's inside first. So I'm going to do 1/2 times 8, 36 plus 20 gives us 56. So this is times 56 plus pi times 6 squared is 36 minus 2 squared is 4. Then we get 1/2, and then times, I'm going to go move down to parentheses now. 8 times 56 gives us 448 plus pi times 36 minus 4 gives us 32. Now I'm going to rewrite this as 1/2 times 448 plus 32 pi, since we normally put pi after the numerical part of the number. And you'll notice here that both these numbers are divisible by 2. So you can see it as using the distributive property when you multiply 1/2 times both of these, or simply just divide both of them by 2, either way. So when we do that here, we get 224. And then when we do it over here, 32 divided by 2 gives us 16 pi. Now we cannot combine these two. I am going to put the 16 pi first. It doesn't really matter if you do that or not. Most people use the pi term first. And so that's the exact area of this figure, this composite figure here, in square inches. Alright, then we do it an approximation. And take 16, multiply by pi, and then add 24, and you should get about 274.3 square inches. That's our approximated area. And so that concludes the problem. We had our formula, our exact area, and our approximated area.